Hello everyone, welcome to a new lecture in the series of deep learning for control. In this lecture, we will be focusing on transformer networks. Here is the overview of this lecture. We will be giving a brief introduction to transformer and also its application in control. Then we discuss the different variants of transformer networks. Transformer is a deep neural network model which is built of transformer blocks. In general, a transformer with B number of blocks can be represented as in equation 1, where we have the predicted output computed using composition of B transformer blocks, and X can be considered as the input data. Each of these transformer blocks consists of a series connection of two networks. The first one is called multi-head self-attention or MHSA network, and the second one is a feedforward neural network. And the distinguishing feature of transformer is the attention mechanism, which we are going to discuss next. The multi-head self-attention or MHSA network is based on the attention operation, and the attention is mainly performed across different samples, where we use an attention matrix AA, which is a matrix of dimension d by d, where d is the number of samples in the training data. This matrix will be a large matrix depending on the size of the number of samples. And we can explain the idea of attention using a simple example, where we consider a data matrix containing two samples of the vector x, where the one in red color is the first sample and the one in blue color is the second sample. And the dataset containing two variables which are denoted by x1 and x2. This x11 and x21 are the first sample of the dataset, and x12 and x22 are the second sample of the dataset. Since we have two samples in the dataset, that attention matrix will be a 2 by 2 matrix, for which the elements are denoted by A, B, C, and D. Now, if we take this operation x times AA, here we right multiplied the dataset with the attention matrix, we obtain the output as in equation 3. When we multiply these two, we will be having x11 into A, which is this term, and then x12 into C, which is this term. And similarly, x21 into A, which is this term, and x22 into C, which is this term. Here, the feature at first sample depends on the input at both the first and second instant. Similarly, second sample of the feature vector depends on both the samples at the first and second instance. This means that the transformed features are a linear combination of the input across samples. This across samples feature makes this transformer model dynamic. We can also use a right multiplication AV, which is multiplied with x into AA. And this right multiplication will take combination across variables or features. Here, this multiplication takes the combination across variables or features, which is happening in other neural networks such as autoencoder, feedforward neural network, etc. This particular operation is the one which makes transformers distinguishable from autoencoder. We can see the idea of self-attention. It is like a particular way of doing the attention operation. And in self-attention, the matrix AA is computed using the data itself. And the transformers are based on multi-head self-attention, where we will be having h number of heads or self-attention stages. And the output of this stage is sum of all the individual attention stages. Here, the small letter h will goes from 1 to capital H. And we have a capital H number of heads or self-attention stages. And by taking the sum over all these stages, we get the output of the MHSA block. Also, at the beginning of each stage, the data is normalized using a normalization function, FNR. It will normalize the input data. And let's say xi denotes the input to the ith transformer block, and y is the output. And we have the output of the bth block, yb, as the predicted output, which is y hat. Then the output of the ith MHSA stage can be defined as xi plus f MHSA of I of xnr I. Here we have a normalized input, apply MHSA block, take a skip connection. And then after that, we have a feed-forward network part as well. So that also has a residual or skip connection. And that feed-forward part takes the output of the MHSA stage, which is denoted by Zi, apply a normalization, then apply a feed-forward network, and takes the residual connection. This Y will be Zi plus Fnn of I of Znri, and this will be the output of the ith transformer block. Now if we apply this along B such blocks, we get a transformer. The loss function for the transformer will be the prediction error, which can be the actual output minus the predicted output. Let the ATF contain all the parameters of the transformer block. Then the optimization problem for transformer is to find the optimal parameter, which minimizes the loss function. The transformers can be used in solving control problems, where it can be used for representing nonlinear dynamic relationships as in equation 10. This is more like a nonlinear ARX model. But here we predict over the entire prediction horizon. So it's like from k plus 1 to k plus np, where np is the prediction horizon. And for that, we use the past value of the output and also the past value of the input as well. Here ny will be the number of past values of the output and nu will be the number of past values of the input. And if we combine all these things, that will be the overall input data to the transformer block. And using that, we can train a model. Recently, a few approaches are proposed where the transformer models are used in MPC. And the challenges in transformer-based control algorithms are it requires a large data set and it is computationally expensive because attention metrics will be very large size if the number of samples are high. And also there are issues with interpretability because it's a data-driven or like black box model. And we also need to ensure stability before using it for safety critical applications. Next, we move on to the different variants of transformer. After the introduction of the transformer, there were many variants were proposed, which are log trans, informer, autoformer, pyroformer, etc., which uses convolution attention, pyramidal attention scheme, etc. And there are other variants such as feedforward, crossformer, and this BERT and GPT are very popular, which are used in for large language model or LLM applications. And these were mainly used for processing text data. And this GPT is the one which is used in the AI-based search engine ChatGPT. Currently, these transformer models are extensively used for mostly for text dataset and also for other datasets such as image, audio, video, etc. Its application in control is going to be an active research area. That leads us to the end of this lecture. Thanks for watching.